Imagine programming as a journey from point A to D. In traditional synchronous programming, we travel in a straight line, stopping at each point before moving to the next. This means if there's a delay at any point, everything pauses until we can move on. Now, asynchronous programming changes the game. It allows us to start tasks at B, C, and D, even if the task at A isn't finished yet. This is like sending out scouts to explore multiple paths at once without waiting for the first scout to return before sending out the next. This way, our program can handle multiple tasks simultaneously, making it more efficient, especially when dealing with operations that have waiting times like loading a web page. And that's the essence of asynchronous programming, making our code more efficient by doing multiple things at once without the unnecessary waiting. So now let's quickly discuss when we should use Async IO, because when we build software, choosing the right concurrency model and picking between Async IO, threads, or processes is crucial for performance and efficiency. Now, Async IO is your choice for tasks that wait a lot, like network requests or reading files. It excels in handling many tasks concurrently without using much CPU power. This makes your application more efficient and responsive when you're waiting on a lot of different tasks. Now, threads are suited for tasks that may need to wait but also share data. They can run in parallel within the same application, making them useful for tasks that are I/O bound but less CPU intensive. I/O meaning input/output. Now, for CPU heavy tasks, processes are the way to go. Each process operates independently, maximizing CPU usage by running in parallel across multiple cores. This is ideal for intensive computations. In summary, choose Async IO for managing many waiting tasks efficiently, threads for parallel tasks that share data with minimal CPU use, and processes for maximizing performance on CPU-intensive tasks. Now that we know when to use Async IO, let's dive into the 5 key concepts that we need to understand. The first concept is the event loop. In Python's Async IO, the event loop is the core that manages and distributes tasks. Think of it as a central hub with tasks circling around it waiting for their turn to be executed. Each task takes its turn in the center, where it's either executed immediately or paused if it's waiting for something like data from the internet. When a task awaits, it steps aside, making room for another task to run, ensuring the loop is always efficiently utilized. Once the awaited operation is complete, the task will resume, ensuring a smooth and responsive program flow. And that's how Async IO's event loop keeps your Python program running efficiently, handling multiple tasks asynchronously. So just a quick pause here for any of you that are serious about becoming software developers. If you want to be like Max, who landed a $70K per year job in just 4 months of work, consider checking out my program with Course Careers. Now, this teaches you the fundamentals of programming, but also lets you pick a specialization taught by an industry expert in front-end, back-end, or DevOps. Beyond that, we even help you prepare your resume. We give you tips to optimize your LinkedIn profile, how to prepare for interviews. We really only succeed if our students actually get jobs. That's the entire goal of the program. So if that's at all of interest to you, we do have a free introduction course that has a ton of value, no obligation, no strings attached. You can check it out for free from the link in the description. So now that we understand what the event loop is, it's time to look at how we create one and then talk about the next important concept, which is coroutines. Now, whenever we start writing asynchronous code in Python, we begin by importing the Async IO module. Now, this is built into Python, you don't need to install it, and for the purpose of this video, I'll be referencing all of the features in Python version 3.11 and above. So if you're using an older version of Python, just make sure you update it because some things have changed in the recent versions. So we begin by importing the module. Then we use the command or the line asyncio.run, and we pass to this something known as a coroutine function, which will return a coroutine object. Now, asyncio.run is going to start our event loop, and it's going to start that by running a coroutine. Now, in our case, there's 2 types of coroutines we're concerned with. We have a coroutine function, which is this right here, and we have what's returned when you call a coroutine function. I know it seems a bit strange, but when you call main like this, when it's defined using this async keyword, this returns to us something known as a coroutine object. Now, the coroutine object is what we need to pass here to asyncio.run. It's going to wait for that to finish, and it's going to start the event loop for us where it handles all of our asynchronous programming. So recap, import the module, define some asynchronous functions, so async, and then you write the function name out, This is known as a coroutine function. You then call the function and pass that to asyncio.run, and that's going to start your event loop and allow you to start running asynchronous code that starts from this entry point. Now, to illustrate this a bit further, let's look at the difference between an asynchronous function, something defined with this async keyword, and a normal function. So watch what happens if I go here and I simply call this function. Some of you may assume that it's simply going to print out start of main coroutine, but you'll see that that's actually not the case. I know that my terminal is a little bit messy here, but it says coroutine main was never awaited. Now, the reason we get that issue is because when we call the function here, what we're actually doing is we're generating a coroutine object. This coroutine object needs to be awaited in order for us to actually get the result of its execution. Now, if we want to see this even more visually, we can actually print out what we get when we call this main function. So let's call it here and notice that we actually get this coroutine object. So when you call a function defined with the async keyword, it returns a coroutine object, and that coroutine object needs to be awaited in order for it to actually execute. So that's why we use the asyncio.run syntax, because this will handle awaiting this coroutine and then allow us to write some more asynchronous code. Now, the next thing that we need to look at is the await keyword. Now, the await keyword is what we can use to await a coroutine and to actually allow it to execute and for us to get the result. The thing is, though, we can only use this await keyword inside of an asynchronous function or inside of a coroutine. So let's write another coroutine and see how we would await it and how we get its result. So now I've included a slightly more complex example where we're actually waiting on a different coroutine just to see how that works. So notice that we have a coroutine up here, and what this is aiming to do is simulate some input-output bound operation. Now, that could be going to the network and retrieving some data, trying to read a file, something that's not controlled by our program that we're going to wait on the result from. So in this case, you can see that we fetch some data, we delay, so we're just sleeping for a certain amount of seconds just to simulate that input-output bound operation. We then get the data and we return it. Now, we know this is a coroutine because we've defined it as an asynchronous function. Now, remember that in order for a coroutine to actually be executed, it needs to be awaited. Now, in this case, what we do is we create a task, and this task is the coroutine object. Now, the coroutine object at this point in time is not yet being executed. And the reason it's not being executed yet is because it hasn't been awaited. What I'm trying to show you is that when you call an asynchronous function, it returns a coroutine. That coroutine needs to be awaited before it will actually start executing. So in this case here, we now await the task. When we await it, it will start executing, and we'll wait for it to finish before we move on to the rest of the code in our program. So let's run the code and see what the output is here. And you can see it says start of main coroutine, data fetched. It then receives the results, and it says the end of the main coroutine. Now let's clear that, and let's look at a slightly different example. So let's take this result code right here. Let me just get rid of this comment. And let's put this actually at the end of this function. So now what we have is print start of main coroutine. We create the coroutine object. We then print end of main routine object. Then we await the coroutine. And I just want to show you the difference in the result that we're going to get. So let's run the code, and notice that we get start of main coroutine, end of main coroutine, and then we get fetching data, data fetched, and then we get the result. Now, the reason we got this is because we only created the coroutine object here. We didn't yet await it. So it wasn't until we hit this line right here that we waited for the execution of this to finish before moving on to the next line. It's really important to understand that fact that a coroutine doesn't start executing until it's awaited or until we wrap it in something like a task, which we're going to look at later. So I've made a slight variation to the last example, and you can see what we're doing now is we're creating two different coroutine objects, and we're then awaiting them. Now, I want you to pause the video and take a guess at what you think the output's going to be and how long you think it will take for this to execute. Go ahead, pause the video. I'm going to run the code now and explain what happens. So when I run this, if we move it up here, you'll see that we get fetching data, ID1, data fetched, ID1. We then receive the result, and then we go ahead and we fetch it for ID2. Now let's clear this and run it one more time. And you can see that it takes 2 seconds. We fetch the first result. It takes another 2 seconds and we fetch the second result. Now this might seem counterintuitive because you may have guessed that when we created these two coroutine objects, they were going to start running concurrently. And that means that it would only take us a total of 2 seconds and we'd immediately get both of the results. But remember, a coroutine doesn't start running until it's awaited. So in this case, we actually wait for the first coroutine to finish, and only once this has finished do we even start executing the second coroutine. Meaning that we haven't really got any performance benefit here, we've just created a way to kind of wait for a task to be finished. That's all we've really learned at this point in time. Now that we understand this concept, we can move over and talk about tasks and see how we can actually speed up an operation like this and run both of these tasks or these coroutines at the same time. So now we're moving on to the next important concept, which is a task. Now, a task is a way to schedule a coroutine to run as soon as possible and to allow us to run multiple coroutines simultaneously. Now, the issue we saw previously is that we needed to wait for one coroutine to finish before we could start executing the next. With a task, we don't have that issue, and as soon as a coroutine is sleeping or it's waiting on something that's not in control of our program, we can move on and start executing another task. We're never going to be executing these tasks at the exact same time. We're not using multiple CPU cores, but if one task isn't doing something, if it's idle, if it's blocked, if it's waiting on something, we can switch over and start working on another task. The whole goal here is that our program is optimizing its efficiency, so we're always attempting to do something, and when we're waiting on something that's not in control of our program, we switch over to another task and start working on that. So here's a quick example that shows you how we would optimize kind of the previous example that we looked at. What we do here is we use the simple create task function. Now, there's a few other ways to make tasks, which I'm going to show you in a second, but this is the simplest. What we do is we say task1 is equal to async io.createTask, and then we pass in here a coroutine object. It's a coroutine object because this is a coroutine function. We call the function, and that returns to us a coroutine. So in this case, we pass an ID, and then we pass some time delay. Now, if this was running synchronously, so if we had to wait for each of these tasks to run, it would take us 2 seconds plus 3 seconds plus 1 second, so a total of 6 seconds for this code to execute. However, you'll see now that what will happen is we'll be able to execute this code in simply 3 seconds, because as soon as one of the tasks is idle and we're waiting on this sleep, we can go and execute or start another task. Now, what I do is I still need to await these tasks to finish, so I just await them all in line here and then collect all of their different results. So let's bring the terminal up and let's run this code and make sure it works. And notice that it starts all 3 coroutines pretty much immediately, and then we get all of the data back at once in about 3 seconds. Again, that differs from if we were to use just the normal coroutines and we didn't create a task. We'd have to wait for each of them to finish before we can move on to the next one. So as a quick recap, when we create a task, we're essentially scheduling a coroutine to run as quickly as possible, and we're allowing multiple coroutines to run at the same time. As soon as one coroutine isn't doing something and it's waiting on some operation, we can switch to another one and start executing that. Now, all of that is handled by the event loop. It's not something we need to manually take care of. However, if we do want to wait on one task to finish before moving to the next one, we can use the await syntax. So it would be possible for me to go here and write some code like this. And now we would see if we execute the code, and we can go ahead and do that, that we'll start the first and the second coroutine, but we won't start the third one until the first and the second one are done. So using asynchronous programming gives us that control and allows us to synchronize our code in whatever manner we see fit. So now we move on to a quick example where I'm going to show you something known as the gather function. Now, the gather function is a quick way to concurrently run multiple coroutines just like we did manually before. So rather than creating a task for every single one of the coroutines using that create task function, we can simply use gather, and it will automatically run these concurrently for us and collect the results in a list. The way it works is that we pass multiple coroutines in here as arguments. These are automatically going to be scheduled to run concurrently, so we don't need to wait for them to finish before we start executing the next one. And then we will gather all of the results in a list in the order in which we provided the coroutines. So the result of this one will be the first element in the list, second element in the list, third element in the list, etc. And it's going to wait for all of them to finish when we use this await keyword, which just simplifies this process for us. That then allows us to have all of the results in one place so we can parse through them using this for loop. So let's go ahead and run this code, and you see that it starts all 3 of our coroutines. We wait 3 seconds, and then we get all of our different results. Now, one thing you should know about gather is that it's not that great at error handling, and it's not going to automatically cancel other coroutines if one of them were to fail. Now, the reason I'm bringing that up is because the next example I show you does actually provide some built-in error handling, which means it's typically preferred over gather, but it's just worth noting that if there is an error that occurs in one of these different coroutines, it won't cancel the other coroutines, which means you could get some weird state in your application if you're not manually handling the different exceptions and errors that could occur. So now we're moving on to the last example in the topic of tasks, where we're talking about something relatively new known as a task group. Now, this is a slightly more preferred way to actually create multiple tasks and to organize them together, and the reason for this is this provides some built-in error handling, and if any of the tasks inside of our task groups were to fail, it will automatically cancel all of the other tasks, which is typically preferable when we are dealing with some advanced errors or some larger applications where we want to be a bit more robust. Now, the fetch data function has not changed at all. All we've done here is we've started using async IO.taskGroup. Now notice that what I'm using here is the async with. Now this is what's known as an asynchronous context manager. You don't need to understand that. You don't have to have seen context managers before. But what this does is give us access to this TG variable. So we create a task group as TG. And now to create a task, we can say TG, our task group, dot create task, just like we did before in that first example. We can create an individual task. We can then add this to something like our tasks list if we care about the result of it. And now once we get by this asynchronous with, so once we get down here to where I have the comment, what happens is all of these tasks will have already been executed. So the idea is this is a little bit cleaner. It's automatically going to execute all of the tasks that we add inside of the task group. Once all of those tasks have finished, then this will stop blocking. When I say stop blocking, that means we can move down to the next line of code. And at this point, we can retrieve all of the different results from our tasks. Now, there's various different ways to go about writing this type of code, but the idea is you simply create a task here. As soon as it's created inside of the task group, we now need to wait for that and all the other tasks to finish before we unblock from this block of code. Then once they're all finished, we move on to the next lines of code. Now, similarly to any other tasks that we looked at before, these are all going to run concurrently, meaning if one task is sleeping, we can go on and we can start another task and work on something else. So those are tasks. Obviously, there's a lot more you can do here, but understand that you run tasks when you want to execute code concurrently and you want multiple different operations to be happening at the same time. So now we're moving on to the fourth important concept, which is a future. Now, it's worth noting that a future is not something that you're expected to write on your own. It's typically utilized in lower level libraries, but it's good to just be familiar with the concept in case you see it in asynchronous programming. So I'll go through this fairly quickly, but really what a future is a promise of a future result. So all it's saying is that a result is to come in the future. You don't know exactly when that's going to be. That's all a future is. So in this case, you can see that we actually create a future and we await its value. What we do is we actually get the event loop. You don't need to do this. You'll probably never write this type of code. We create our own future. We then have a new task that we create using async IO, and you can see the task is set future result. Inside here, we wait for 2 seconds. So this is some blocking operation. And then we set the result of the future and we print out the result. Here, we await the future and then we print the result. Now notice we didn't actually await the task to finish, we awaited the future object. So inside of the task, we set the value of the future and we awaited that, which means as soon as we get the value of the future, this task may or may not actually be complete. So this is slightly different than using a task. When we use a future, we're just waiting for some value to be available. We're not waiting for an entire task or an entire coroutine to finish. That's all I really want to show you here. I don't want to get into too many details. That's a future, really just a promise of an eventual result. So now we're moving on and talking about synchronization primitives. Now these are tools that allow us to synchronize the execution of various coroutines, especially when we have larger, more complicated programs. Now let's look at this example so we can understand how we use the first synchronization tool, which is lock. Let's say that we have some shared resource. Maybe this is a database, maybe it's a table, maybe it's a file, it doesn't matter what it is, but the idea is that it might take a fair amount of time for us to actually modify or do some operation on this shared resource, and we want to make sure that no two coroutines are working on this at the same time. The reason for that is if two coroutines were, say, modifying the same file, if they're writing something to the database, we could get some kind of error where we get a mutated state or just weird results end up occurring because we have kind of different operations happening at different times and they're simultaneously occurring when we want to really wait for one entire operation to finish before the next one completes. That might seem a little bit confusing, but the idea is we have something and we want to lock it off and only be using it from one coroutine at a time. So what we can do for that is we can create a lock. Now, when we create a lock, we have the ability to acquire the lock, and we do that with this code right here, which is async with lock. Now, this again is an asynchronous context manager, and what this will do is it will check if any other coroutine is currently using the lock. If it is, it's going to wait until that coroutine is finished. If it's not, it's going to go into this block of code. Now, the idea is whatever we put inside of this context manager needs to finish executing before the lock will be released, which means we can do some critical part of modification. We can have some kind of code occurring in here that we know will happen all at once before we move on to a different task or to a different coroutine. The reason that's important is because we have something like an await. Maybe we're awaiting a network operation, a save, something else that could trigger a different task to start running. In this case, we're saying, hey, within this lock, wait for all of this to finish before we release the lock, which means that even though another task could potentially be executing when this sleep occurs, it can't start executing this critical part of code until all of this is finished and the lock is released. So all the lock is really doing is it's synchronizing our different coroutines so that they can't be using this block of code or executing this block of code while another coroutine is executing it. That's all it's doing. It's locking off access to, in this case, a critical resource that we only want to be accessed one at a time. So in this case, you can see that we create 5 different instances of this coroutine. We then are accessing the lock. And then again, once we get down here, we're going to release it. So if we bring up the terminal here and we start executing this, you'll see that we have resource before modification, resource after, before, after, before, after. And the idea is, even though that we've executed these coroutines concurrently, we're gating them off and we're locking their access to this resource so that only one can be accessing it at a time. Moving on, the next synchronization primitive to cover is known as the semaphore. Now, a semaphore is something that works very similarly to a lock. However, it allows multiple coroutines to have access to the same object at the same time, but we can decide how many we want that to be. So in this case, we create a semaphore and we give it a limit of 2. That means that only 2 coroutines can access some resource at the exact same time. And the reason we would do that is to make sure that we kind of throttle our program and we don't overload some kind of resource. So it's possible that we're going to send a bunch of different network requests. We can do a few of them at the same time, but we can't do maybe 1,000 or 10,000 at the same time. So in that case, we would create a semaphore. We'd say, okay, our limit is maybe 5 at a time. And this way, now we have the event loop automatically handle this, so we throttle our code intentionally to only send maximum 5 requests at a time. Anyways, let's bring up our terminal here and run this code. So Python 3 semaphore.py, and you can see that we can access the resource kind of 2 at a time and modify it, but we can't have any more than that. Now moving on to the last primitive we're going to talk about, this is the event. Now the event is something that's a little bit more basic and allows us to do some simpler synchronization. In this case, we can create an event, and what we can do is we can await the event to be set, and we can set the event. Now this acts as a simple Boolean flag, and it allows us to block other areas of our code until we've set this flag to be true. So it's really just like setting a variable to true or false. In this case, it's just doing it in the asynchronous way. So you can see we have some setter function. Maybe it takes 2 seconds to be able to set some result. We then set the result, and as soon as that result has been set, we can come up here, we await that, so we wait for this to finish, and then we can go ahead and print the event has been set, continue execution. So we can bring this up here and quickly have a look at this. So Python 3, if we spell that correctly, event.py, and you'll see it says awaiting the event to be set, event has been set, continuing the execution. Okay, pretty straightforward. It's just a Boolean flag that allows us to wait at certain points in our program. There's lots of different times when you would want to use this, but I just wanted to quickly show you that we do have something like this that exists. Now, there is another type of primitive here that's a bit more complicated called the condition. I'm not going to get into that in this video. In fact, I'm going to leave the video here. If you guys enjoyed this, make sure you leave a like, subscribe to the channel, and consider checking out my premium software development course with Course Careers if you enjoy this teaching style and you're serious about becoming a developer. Anyways, I will see you guys in another YouTube video.